All right, welcome back. Today we're going to pick up where we left off. Um, Last time we introduced Lewis structures. We said the Lewis dot structure, it was a way to represent the number of valence electrons in an atom. If you looked at sodium, we had sodium, the chemical symbol with one dot. That one dot represented the one valence electron in sodium. Again, that's the electron in the outer shell. And then the chemical symbol sodium represents the protons and neutrons and core electrons, the electrons other than the outer shell electron. So we brought in from the last chapter the discussion on ionization energy and electron affinity. The metals tend to have low ionization energies. They're on the left hand side of the periodic table, which means it's much more much easier to remove an electron from a metal than the high ionization energy nonmetals on the right side of the periodic table. For electron affinities, the metals have low electron affinities. They don't release much energy if they accept an electron, whereas the nonmetals, again, with the higher effective nuclear charge, they tend to accept an extra electron and release quite a bit of energy. So knowing those things from the last chapter and knowing about Lewis dot structures, we can symbolize the bonding that occurs between a metal and a nonmetal and a nonmetal and another nonmetal. So just to kind of recap that, we had sodium and it has one dot which represents the valence electron. We're going to bond that to chlorine, which has a total of 7 valence electrons. And because chlorine has a high ionization energy and a high electron affinity, this electron from sodium, which has a low ionization energy, is going to be removed from sodium. It's going to attach itself to the chlorine, and that's going to yield a sodium ion. And again, for a Lewis dot structure, you take the dots away, you show the charge. And for the nonmetal that gains the electron, you show all the dots, and then you got the gaining of the one here. You put that in brackets and you put the charge outside the brackets. So this is the way sodium chloride is formed, and it is the electrostatic attraction, this positive charge and this negative charge, that creates the force that holds these two ions together, and we call that ionic bonding. So we talked about that in our last presentation. Now, on the other hand, if I take something like fluorine, and fluorine has 7 valence electrons, 7 electrons in the outer shell, so it looks like this, and I bond that with another fluorine. Well, both fluorines have the same electron affinity. They have the same ionization energy. And so one fluorine doesn't have the ability to pull an electron off of the other fluorine. So in this case, this electron and this electron from the other fluorine are going to be shared to create the bond that holds the two fluorines together. And those shared electrons are represented by the dots between the two chemical symbols. So these are the two shared electrons. And then we fill in the rest of the valence electrons for fluorine and the rest of the valence electrons here for fluorine. And so what we see is each fluorine feels like it has 8 because it's sharing that pair. And that the thing about 8, it's called the octet rule, and the octet rule says that elements tend to lose or gain electrons to become isoelectronic with the noble gas, which means that it has 8 electrons in the outer shell. And we see that from period 2 on. Remember, the first shell can only hold 2 electrons, so helium is satisfied with 2 electrons in the first shell. And so if we're talking about something like hydrogen, hydrogen's going to be satisfied with sharing its electron with another hydrogen, and both hydrogens feel like they have 2 electrons around them. So that's a recap of what we did in our last presentation. Today we are going to talk about unequal sharing of the electrons. So let's just erase this part, and let's look at what would happen when I bond something like hydrogen to fluorine. So here's hydrogen with its 1 valence electron, and then there's fluorine with its 7 valence electrons. So hydrogen's on the far left of the periodic table, and fluorine's on the right-hand side of the periodic table. They are both nonmetals. And yes, hydrogen's electron is going to go here. And so by doing that, hydrogen is sharing its electron with the fluorine's electron, and that creates a bond. And then the fluorine is satisfied that it has 8 electrons around it. So this is covalent bonding. How do you know it's covalent bonding? When you see electrons in between 2 atoms, you don't see that down here with the ionic compound with sodium chloride here. You don't see any dots like being shared. There's a bracket here, and there's actual charges, and you don't see actual charges up here. This is a covalent bond, but it's a subcategory, and that is it's unequal sharing of the electrons. We know that fluorine has a higher electron affinity than hydrogen, and so these electrons are not being shared equally between the hydrogen and the fluorine. And so what we see is this side becomes partially negatively charged, partial, that's what this is, a lowercase delta, and this side becomes partially positive charge. That means the electrons as a whole are spending a lot more time around the fluorine than around the hydrogen, and so less electron density around the hydrogen gives it a partially positive charge, and less electron density around the fluorine gives it a partially negative charge. So factors that come into play here are ionization energy, electron affinity, size of the atom, and it can be even more complicated than that, but those are the 3 major factors for us. And so instead of talking about electron affinity, ionization energy, and size of the atom, Linus Pauling came up with this theory called electronegativity. So electronegativity is a measure of the ability of an atom to attract electrons in a chemical bond. So this happens when 2 atoms bond together. What is the ability of one atom to attract electrons from another atom? And the greater the electronegativity, the more it has the ability to attract electrons from another atom that is of low electronegativity. So they talk about consider the covalent bond as a competition between the electrons. Like we see up here, fluorine is a lot more electronegative than hydrogen, so it pulls the electrons away from the hydrogen. So let's look at an electronegativity table. So the next slide, we have the electronegativity table. And what I want you to get out of this table is that the trend is electronegativity increases as we go from left to right. And again, that makes sense. The atom is getting smaller as we go from left to right. The electron affinity is increasing, and the ionization energy is increasing as well. So fluorine doesn't want to lose an electron. It wants to gain an electron. Just wants to gain 1 extra electron, and it becomes isoelectronic with the noble gas. So electron affinity increases up to fluorine. And because we're adding more shells to the atom and the electrons are getting further from the nucleus, electron affinity or ionization energy decreases as we go from top to bottom. All right. So you're going to see the most electronegative element on the periodic table here is fluorine. And the least electronegative elements are going to be down here in the lower left-hand corner, which is a metal. So that's what you see here. Is metals tend to have low electronegativities, and nonmetals tend to have high electronegativities. And notice the noble gases aren't in the picture because the noble gases, we don't think of them having an electronegativity in that they don't want to gain an extra electron because it would have to go into an upper shell. And we saw that with the electron affinities. It generally requires energy to add an electron to a noble gas. So I want you to memorize the trend that it increases as you go across and decreases as you go down. There are some electronegativities I think are worth memorizing. I think hydrogen should be memorized. I think carbon should be memorized, and nitrogen, and oxygen, and fluorine, and chlorine, and sulfur. And the reason why I think you should memorize these is because they come up so frequently, and they will save you a lot of time in thinking about what type of bonding is occurring, and to explain why there's such a bond polarity. Because what happens here is when that hydrogen bonds with the fluorine, the electron, overall, we would draw an arrow like this to say this is a vector, and this is the positive end, and this is the negative end. And the electrons are moving more so to the fluorine than the hydrogen. And that creates what we call a polar bond, which means polar means it's got a positive and negative end, and bond, we know it's a covalent bond, so you could call it a polar covalent bond. A lot of people just say polar bond. As soon as you hear the word polar bond, we generally believe it's a covalent bond. Otherwise, we call it an ionic bond. And you say, well, how am I supposed to use this? Well, let's look at the next slide. You are going to determine how strong the polar covalent bond is, and you say, why do I need to know this? Well, this has implications in melting points, boiling points, viscosity, which is resistant to flow, surface tension. These are all macro properties that we'll be talking about later on. So one of the things you're going to learn from this is that water is a polar, it has polar covalent bonds. It also is a polar molecule, and that's why water freezes at such a high temperature, really, 0 degrees versus negative 20 degrees. So that's where the implication of this is going to be important. So electronegativity calculations, you look on the table and just take, you don't have to take the highest one first. They made it easy on you by, the bottom line is the difference in electronegativity has to be an absolute value. It's not positive or negative. So they just take the more electronegative fluorine, subtract the lower electronegative hydrogen, and the difference is 1.8. For hydrogen and chlorine, the difference is 3.2 minus 2.2. Notice these are both for hydrogen, and the difference is only 1.0. So the hydrogen fluoride bond is much stronger or more polar than the hydrogen chloride bond. So that's what we're going to be doing, is electronegativity calculations to determine the polarity of the bond. The greater the difference in electronegativity, the more likely it is to be polar. So here's my general rule of thumb. And if the difference in electronegativity, and this is important, I want you to write this down, if it's between 0 and 0.4, we generally call this a non-polar bond. Now, non-polar means there's not a positive and negative end, and that this is, again, a covalent bond. So this would be like where you bond hydrogen with another hydrogen. So they both have the same electronegativity, so that would be 2.2 minus 2.2 for a difference of 0. That's a pure covalent bond. You say, well, does it ever happen with something different than that? Yeah, later we're going to see, like if you bond carbon with sulfur, we're going to find out its Lewis structure looks like this. If we go back to the previous slide and look at the electronegativities of carbon and sulfur, you would see that carbon is 2.6 and sulfur is 2.6. So you see that 2.6 and 2.6 for a difference of 0. So again, because there's a difference of 0 here, 2.6 minus 2.6 for each carbon-sulfur bond. We're evaluating these individually. Difference is 0, therefore it's a nonpolar bond. The one that's a little tricky, I guess, is carbon and hydrogen. So we're going to be talking about methane a lot, and so we're going to find out the Lewis structure for methane looks like this. And if I want to evaluate this bond here, the electronegativity of carbon we just saw was 2.6 minus 2.2, which equals 0.4. So we generally think of that as a nonpolar bond. So 0 to 0 to 0.4 is nonpolar. Let's write that down here. 0 to 0.4, nonpolar. All right. Then we get above 0.4 and we go up to 2.0. This would be called a polar bond. And that means there's going to be a positive and negative end to the bond. And then above 2.0, we would say that substance is ionic. So that means total electron separation from the lower electronegative element and an electron acceptance from the higher electronegative element. So that's why we use this. It's a way to determine how metallic in character is this compound. Like if it's purely covalent, we would call that a molecular compound, that there's equal sharing of the electrons. When we get to above 2.0, we say, oh, this is an ionic compound that if I put this in water, it's going to separate into its positive and negative ions, and it's going to conduct electricity. So that's why this is important. It gives us an indication as to how metallic, or how is this substance going to behave. Is it going to behave as a covalent compound or a ionic compound? So there are two naming systems we're going to use in this class. And in this section, I just want to say there's a lot of memorization. It's not hard. It's just something you got to do each day. You got to make some cards. Some of you've already had this. If you had chemistry in high school and you had a good teacher, they probably had you memorize this stuff already, and you're just refreshing your memory. If you've never had chemistry, that's okay. That's what this class is about. But you do need to memorize what I'm going to tell you to memorize. This is a big hurdle in this class. I find a lot of students, they don't take the time to memorize. They get dinged on this from here on out to the rest of the semester. If you're taking the lab, you get dinged in there as well. And it's going to hurt you if you're planning to take general college chemistry next. So take the time to memorize. I do have in my announcement the Anki app. It's an electronic flashcard. You may want to try that. If you don't want to use that, just make you some flashcards. Put the chemical symbol on one side and the name on the other side, and go through them until you have mastered these. And it does take a while. That's why you need to start now. And that's why I have a video on naming. So this is really important. It's going to be used from here on out after we get through this chapter. And you don't have time to look up every compound. So it's important that you learn these two naming systems. So first of all, what I want to point out is there are two naming systems, and they are different. There's a naming system for ionic compounds, and there's a naming system for covalent compounds. And don't mix these up. They're totally different. And I find what happens is once we learn how to do covalent compounds, students want to use the covalent naming system on ionic compounds, and it doesn't work that way. And the reason it doesn't work that way is, let's look at a compound like calcium nitride. All right, so I'm going to say calcium nitride. So you would say, oh, calcium, that's Ca, and nitrogen is N. So when you look at the periodic table, calcium would form a 2 positive ion because it's in group 2. It's got 2 valence electrons. It loses those 2 valence electrons to become isoelectronic with argon. And nitrogen, being in period 2 and group 15, would like to gain 3 electrons to become isoelectronic with neon. So that's how we know the charges on these two ions. Calcium group 2, all group 2 metal ions are going to be 2 positive, and nitrogen being in group 15, it's got 5 valence electrons. It's going to gain 3 electrons to get a full outer shell of 8. So both of these numbers go into 6, and so I need 3 calcium, 2 positive ions, and 2 nitrogen, 3 negative ions to have a neutral compound. So my final chemical formula is calcium with a subscript 3 and nitrogen with a subscript 2. That means 3 calciums as these subscripts. That means there are 3 calcium ions bonded to 2 nitrogens. Now, I don't have to tell the person there's 3 calcium and 2 nitrogen because that's determined by the charges, and that both of these go into the number 6. So we just call it calcium nitride. But what I hear students do is they use the covalent system of naming and say tricalcium dinitride or dinitrogen. First of all, you got an IDE ending, and second of all, you don't have to say how many calcium or nitrogen because it's determined how many calcium and nitrogen you need by the charges on the ions. Now, I agree. If you have something like N2O5, so nitrogen and oxygen bonded together, these are 2 nonmetals. So here, because they're 2 nonmetals and they're not charged ions, you have to say how many of each substance you have. So you would say dinitrogen, which would mean 2 nitrogens. And then oxygen, you got 5, so you might be thinking like pentagon. So it's penta, but because oxygen begins with a vowel, you say oxide. So you drop the A off penta and say pentoxide. So different naming system for nonmetals, and the reason why there are no charges to go by. Ionic compounds, you don't say how many of each ion you have because you have the charges to determine how many of each ion you need. So that's it in a nutshell, but let's go through it. So a formula, when we say the word formula, we're talking about ionic compounds. If we're calling them molecules, we're generally talking about covalent compounds. I don't know if this book makes a hard distinction on this. They just say a formula represents the fundamental chemical symbols and the subscripts. But generally when we say the word formula, formula unit, we're talking about ionic compounds. This is saying if there's only one of each element present, like in sodium chloride, we don't put a subscript 1 in 1. It's understood to be 1 to 1 here. All right, so metals with nonmetals usually form ionic compounds. Metals are going to form positive ions called cations. The way to remember that, cation is a T, looks like a positive, and nonmetals form negative ions called anions. Again, we know this because of the high electron affinities and the high electronegativities of the nonmetals. Now, the next thing here is the formula for an ionic compound always has to be in the simplest whole number ratio. So let me show you why when I say you need to think about what numbers both things go into. So let's say we're going to bond 10. Sn is the symbol for 10, and it comes in a 4 positive charge state. And I'm going to bond that to sulfur, which is a nonmetal, and that forms a -2 ion. So I see students every once in a while, they've had some chemistry and they learn this crisscross method. So they put the 4 here and the 2 here, and they would come up with the chemical formula of SN2S4. Well, that would be incorrect because the formula for ionic compounds always has to be in the smallest whole number ratio. So a better way to do this is to say, okay, 10 is 4 positive, sulfur is 2 negative, both numbers go into 4. So I need 1 10 and I need 2 sulfurs for that to be electrically neutral. 2 -2 charges, 1 4 positive charge. This is the correct chemical formula. So again, ionic compounds, this would be incorrect because it's not in the smallest whole number ratio. By thinking about what numbers go into both of the charged ions, in this case 4, you won't make that mistake. You should always end up with the simplest whole number ratio. All right, so here's the rules. Determine the charge of each ion. Usually it's related to the group number. Nonmetals tend to add electrons to get a full outer shell of 8 from the group number. Metals tend to lose the electrons in the outer shell. When you add the cations and anions together, the net charge should be 0. So everything we've seen, when we add the positive and negative together, the positive and negative ions together, the cations and anions, we get overall 0 for a charge. So let's do some naming here. So what I would tell you to do is stop the video at this point and try these on your own, and then start the video again and see if you get the correct answer. So sodium, you need to know at this point that sodium is Na, that oxygen is O, this is a metal with a non-metal. Sodium's a metal, so sodium's in group 1, it's going to form a positive 1 ion. And oxygen being in group 16 and a non-metal forms a negative 2 ion. Both of these numbers go into 2, so you will need 2 sodiums and 1 oxygen. And that would be the correct formula for sodium oxide. So that's the way we name it. You name the metal by its full name, and you change the non-metal to IDE ending. And that's important. Oxygen and oxide have totally different chemical and physical properties. So make sure you understand these have an IDE ending. That tells you it's not the same thing as oxygen. All right, next one, lithium and bromine. So you got lithium. It's also in group 1, so it's going to form a positive 1 ion. And bromine is in group 17 or 7A, and it just needs 1 extra electron to become isoelectronic with the noble gas and to have a full outer shell of 8, called the octet rule. So again, this is positive 1, this is negative 1. Both of these go into 1, so lithium bromide's formula is just LiBr. Really easy. Next one, aluminum. Aluminum is a metal. Oxygen is a non-metal. Aluminum is in group 13. It's going to lose all of its outer shell electrons, 3 positive. Oxygen, group 16, it's going to gain 2 electrons to have a full outer shell of 8. 3 and 2 both go into 6. I need 2 aluminums, and I need 3 oxygens to have an electrically neutral compound. Net charge equal to 0. All right, 2 times 3 positive plus 3 times 2 negative will give me overall charge of 0. And then the last one, barium. Barium's in group 2, so it's going to form a 2 positive ion. Fluorine is in group 17. It's going to form a negative 1 ion. Both go into 2. I need 1 barium and 2 fluoride. So barium fluoride would be the correct answer. So I hope that's helpful. If you need more practice, definitely watch my video on nomenclature. That does the full naming for ionic and covalent compounds. All right, so they give you some examples. I'm not going to go through these. Pretty much the same thing we've just seen. Name the cation by its full metal name. Change the anion to an IDE ending. And again, we don't tell people how many of each ion are present because this is all determined by the charges on the ions. All right, pretty easy. All right, so this is where students have some difficulty, and these are generally occurring in the transition metals. And what happens here is iron can come in a 2 positive charge form, and it can also come in a 3 positive charge form. So we have to tell people which one do we have. So when I look at a compound like this, what I have to do is I have to say, oh, chlorine is a negative 1 ion. And so if that's a negative 1 ion and I have 3 of them, this iron has to be the 3 positive form. So to convey to a person that I have iron 3 chloride, not iron 2 chloride, which would look like this, I have to say, I have to put a Roman numeral in parentheses between the metal name and the non-metal name. All right? So that's why this is called iron 3 chloride. The Roman numeral represents the charge on the ion. It does not represent the number of ions you have. That's what I see students make a mistake on. The Roman numeral represents the charge on the metal ion, not how many you have. So this one, the chlorine is negative, and there's two of them. So that means this iron has to be a 2 positive ion. So this is called iron Roman numeral 2. So this is called the new system, or the common name for it is also stock system. So if they ask you for the new system or stock system of naming, they are expecting you to write the Roman numeral between the metal and non-metal. And this occurs generally with the transition metals. Now, there are some that I want you to know, and they're in the nomenclature video. I'm just having you memorize iron, copper, it's not the best copper, tin, lead, and mercury. So look at my nomenclature video. I point those out, but I do want you to know the stock system name for each of those. So that's the stock system name. This slide shows you the common name. So the common name is still used today. So if you have a tube of Crest toothpaste, you will see one of the compounds in your Crest toothpaste is stannous fluoride. What does stannous fluoride mean? Well, stannous means SN, and fluorine is F, and we know it's a -1 charge. Well, what's the charge on the tin, which is the stannous? Well, tin comes in 2 charge forms. It comes in a 2 positive, and it comes in a 4 positive charge form. The lower charge form gets the OUS ending. All right, the lower charge form. So when somebody says stannous fluoride, I know it's tin with a 2 positive charge. Fluorine's a -1 charge. Both of these numbers go into 2, and the correct chemical formula is this. Now, stannic fluoride, let's say it was called stannic fluoride. Stannic would be the higher charge form, which would be 4 positive here, and a still -1 charge on the fluoride ion. But the chemical formula would be SNF4, which is a totally different compound than in SNF2. So I want you to know the higher charge form and lower charge form for the 5 elements that I pointed out on the last slide. Let's go back. I want you to memorize the higher and lower charge form. So tin comes in a 2 positive and a 3 positive form. Copper comes in a 1 positive and a 2 positive form. Tin comes in a 2 positive and 4 positive. Lead in the same group, same thing, 2 positive and 4 positive. The mercury is tricky. Mercury comes in 2 mercuries bonded together with a 2 positive charge. That's the lower charge form. And then there's mercury with the 2 positive, just 1 mercury with the 2 positive form. So again, I know that's fast, but watch the nomenclature video that's posted in the announcements and on my Professor Chemistry website, YouTube channel to see that. You do need to know those, and you need to know the old system. And you say, why do I need to know the old system? If you're thinking about doing any career in allied health, they still use the old system when they describe compounds, ionic compounds, like the stannous fluoride. So here are some of those, and just look at them. This is a nice table because it shows both the stock system, as I called it, the new system or stock system, and then the common system. And these are the same compounds. It's just we're looking at the stock system versus the common system. and that's two of them. And then the other two are tin and lead, and again, tin and lead both come in a 2 positive form and a 4 positive form. All right, and so that's two more that you need to memorize. And this is lead. Guy works on your pipes is called a plumber. That's where we get the word plumber. Plumbus or plumbite is the lead ore, and so plumber is that is derived from that Greek name, so that's why it's PB for lead. So those are easy, I think, because both of these are in. The reason why these are easy to remember, if you look at that, you're looking at the outer shell for tin, and you go, okay, it's in period 5, and it's, I mean, if we just look at it, in the outer shell, it's 5s2, 5p2. So these two electrons come off, that makes it 10, 2 positive, and then these two electrons come off, and that makes it 10, 4 positive. So the same thing with lead being in the same group, that's why they form a 2 positive and 4 positive ions. These, I don't know why this slide's really here. It's really easy. It's just saying monoatomic metal ions. They just, all you do is name them by the name of the metal and say ion. Sodium ion, potassium ion. So it's not really memorization here. It's just the metal and you add ion to it. So when I say magnesium, I mean Mg, but when I say magnesium ion, I say it's Mg2 positive. All right. The nonmetals, the anions, they all end in IDE. That's the key here. They all end in IDE. So again, the difference between nitrogen and nitride is that this is a neutral atom and this is an ion. So if it's got an IDE ending on it, then we're talking about an anion of that particular nonmetal. That's pretty easy. That's a pretty simple slide. All right. Here's where students have the most difficulty, and that is polyatomic ions. So polyatomic ions are two or more atoms bonded together that have a positive or negative charge. All right, so two or more different elements, I should say, bonded together. Or it could be two atoms. Yeah, it could be two or more different atoms too. So let's look at this. So here's the ammonium ion. So it's got nitrogen and hydrogen bonded to it, and it also has a charge. So we're not looking at just like nitrogen, which is 3 negative. We're looking at nitrogen bonded with another element, and it has a charge. So that's called a polyatomic ion, and they have their own names. So same thing here. Sulfur is 2 negative, oxygen's a 2 negative ion, but when they combine together, they form SO4, 2 negative, and that's called the sulfate ion. So polyatomic ions, two or more different atoms bonded to, or two or more atoms bonded together with a charge. And there's quite a bit of memorization here. So this is it. Now, it looks like a lot to memorize, but it's not. Let me show you how I can show you some tricks on how to memorize this one. So this one, you just flat out memorize. Same thing for this one. All right, let's look at these two here. I memorized this one, NO3 negative, nitrogen with 3 oxygen with a negative charge. I'll call that nitrate. If I knock an oxygen off and the charge still remains the same, it has an ITE ending. It's called nitrite. So I just memorized this one and know that when I knock an oxygen off, it's nitrite. Same thing here. I memorized sulfate, SO4, 2 negative, sulfate, ATE, and if I knock an oxygen off, it becomes sulfite. And if I have sulfate and I add a hydrogen to it, I know hydrogen would be like a positive 1 ion if I added that to that. And so that's why it's a negative charge. I lost one of the negative charges because I've added a proton, and so we just call that hydrogen sulfate. That's not hard to memorize either. So if you add a hydrogen ion to a polyatomic ion, you know the negativity is going to drop by 1. Okay. Then we have hydroxide. Just memorize that flat out. Same thing here. Same thing for phosphate. Now watch the phosphate. Here again, you got phosphate. You memorize this one, PO43 negative. If you add a hydrogen to it, that's like a H positive. That's why it's -2 now. And that's called hydrogen phosphate. And if you add another hydrogen, now the charge drops to -1 because each of these hydrogens is positive. And we do have to use the word di here, dihydrogen, to say there's 2 hydrogens attached to the phosphate. These are really important in biology or in allied health, so make sure you know those. Those are really important. To me, this is what you're going to take in a biology class right here. You need to know those. ATP cycle and some of those things, we're going to have some of that in there. This is a really important one, carbonate, another big one in allied health. You just memorize CO3 2 negative. If you add a hydrogen, it's now HCO3 negative. You lost one of the, you've gained a proton, as so to speak. That's the way we should say it. Gained a positive proton. That's why it's a -1 charge. And we call that, the modern systems call it hydrogen carbonate. But this has been around so long, it's got an old common name, which is called bicarbonate. So like sodium bicarbonate you get in your store, Arm & Hammer baking soda, sodium bicarbonate. Now, this is the one that freaks students out the most, is this series right here. But it's real easy. And it works for not only chlorine, it works for chlorine, it works for bromine, it works for iodine. So when we take chlorine and bond it to oxygen, if we have 3 oxygens, or if we take bromine and bond 3 oxygens to it, it has a -1 charge. And then in this case, it's called chlorate. That's the one I memorize. If I knock an oxygen off and the charge remains the same, it has an ITE ending. It's called chlorite. Now, what happens if I knock another oxygen off and I only have 1 oxygen, same charge but only 1 oxygen? It's called hypochlorite. So you know hypoglycemia, less sugar. Hypochlorite means less oxygen. Hypo. And then if I have the chlorate and I add an oxygen to it, then, and the charge remains the same, we would call that hyperchlorate, but because we don't say hyper, we call it perchlorate. All right, but it probably should have called it hyperchlorate, but we call it perchlorate. All right, so that works for chlorine. Do the same thing. You memorize bromate. If you knock an oxygen off, it becomes bromite. Knock another oxygen off, it becomes hypobromite. Add an oxygen to bromate, BrO4 negative, and it becomes perbromate. All right, so it's not as much memorization as you think. It's once you know how to do that sequence, you're done. You've understood it. Acetate, this is one of the most missed ones, but this is really important. This is a byproduct a lot of times of decompositions in biology, so acetate really important. Permanganate, sometimes important in a lab. It's a good oxidizing agent. We don't use this in the lab anymore. I'm not as interested in you memorizing that one. This one's okay. You memorize it if you want to. And then the last one's really important, peroxides. So here is a polyatomic ion with 2 of the same atom. That's why I was kind of flipping. Does that have to be 2 different atoms? No. Here's 2 atoms of the same thing bonded together with a -2 charge. So you know you got oxide, O2 negative. This is 2 oxygens with a 2 negative charge. So it's effectively like each oxygen has a 1 negative oxidation state, as we call it. And so that's called a peroxide. And you know peroxides, hydrogen peroxide, you pour that on a cut and it starts fizzing. That's the oxygen coming out of it. So these are important. And you have to memorize them. There's no getting around it. The sooner you get them memorized, the easier you're going to have through the rest of the class. You need to memorize them for the test coming up. Spend some time on this, a little each day. Don't just try to cram it. You can't cram this. You learn. Let's say you try to learn, 5 of these a day. I think you can handle that, 5 a day. And once you get this down, you have it with you the rest of your life. So just spend the time with this. Spend the time with this so that you can be successful through the rest of the class. It's not as much memorization as you think when you think about the little things we learned like nitrate, nitrite, sulfate, sulfite. So here's where we come. This is, and let me just say, the reason why you have to know those polyatomic ions, when we start talking about acids and bases, when we talk about acids, if the polyatomic ion ends in 8, like sulfate, SO42 negative, we know that 2 hydrogen ions have to attach to that to make this neutral. And so when we do that, this acid is called sulfuric acid. Sulfuric acid. Well, if we have H2SO3, we know SO3 is the sulfide ion, and so this is called sulfurous acid. So if you know the ion ends in I, the acid ends in OUS. If the ion ends in 8, like sulfate up here, the acid ends in IC. So this is going to hit you different places if you don't memorize this. So I can't stress enough, you have to spend the time memorizing these polyatomic ions. Because once you do that, you're going to just, you'll know that NH4 is ammonium. So this is the ammonium chloride compound. This is barium. And then SO4 I recognize as the sulfate ion. So what we're having here is, this is a metal, this is a polyatomic ion. Up here we had a polyatomic ion and we had a nonmetal. This one we have a metal, and here's where it gets tricky. If you don't know what the charge is on the nitrate, then you don't have a shot as to what the charge is on the iron. Because if the nitrate you said was 2 negative, 2 times 3 would be 6 negative, so you'd say iron 6 positive. It doesn't work that way. Knowing that the nitrate is -1 charge and you have 3 of them, that's 3 negative. That means this iron is 3 positive. So you would call this iron Roman numeral 3 nitrate. Or you would call it ferric. If you want to know what the common name is, you would call it ferric nitrate. That's why you have to know both the common name and the stock system name. Both of those are important. This one gets a little trickier. Copper is one of those substances that comes in more than one charge form, a +1 and +2. You have to recognize this is the bicarbonate or hydrogen carbonate ion, and it's a -1 charge, so that means this copper is +1. So you would call this copper Roman numeral 1. I'm going to, if I was using Roman numeral 1, I would say hydrogen carbonate. That would be the full new name. Now, they probably would say hydrogen bicarbonate, but if I was going to do that, I would call it cuprous, the lower charge form, bicarbonate. That would be the common name. So, either way, both of those are correct. I would say your book probably calls this copper 1 bicarbonate, but if you're going to stick with the common name, that's the whole common name. And then the last one is just calcium, name the metal, and then the non-metal is hydroxide. And again, that's all it is, calcium hydroxide. You don't say calcium dihydroxide. Why? This is understood to be a -1 polyatomic ion. This is understood to be a 2 positive ion. You need 2 of these for every one of these, and it's just called calcium hydroxide. All right, so the next thing is writing the formulas. You're given the charges, you have to write the formula. So instead of giving the formula and giving the name, or giving the name, write the formula, here we're going to be given the formula and you write the name. So in this case, barium's 2 positive, chloride's -1. You need 2 chlorides to go with every barium, so it's BaCl2. All right, so let's look at these. So sodium sulfate is the name. So sodium is a +1 ion, and sulfate is a -2 ion. Both of these go into 2, so you would write this as Na2SO4. You need 2 of these because it's 1 positive for every one of these, which is 2 negative. So sodium sulfate. Ammonium sulfide, NH4 positive is the polyatomic ion. Sulfide being in group 16 forms a -2 ion because it wants to gain 2 electrons to get a full outer shell of 8. Both of these go into the number 2. You need 2 of the first polyatomic ion. So if you need more than one polyatomic ion, you put it in parentheses. You put the number outside the parentheses of those polyatomic ions that you need, and then you finish it off with the sulfur. You only use parentheses when you have more than one of the polyatomic ion. Magnesium phosphate, this is a good one. Magnesium, group 2, forms a 2 positive ion. Phosphate, polyatomic ion with a -3 charge. Both of these go into 6. So I need 2 magnesiums to get, three magnesiums. That's not too good. 3 magnesium, 3 times 2 gives me 6 positive. And then phosphates, I need, that's not my best 4 either. Phosphates, I need 2 of those. 2 times 3 gives me 6 negative. And then the last one, even though I don't have you memorize this, you should be able to do this one. You should say, okay, chromium, Roman numeral 2 means chromium with a 2 positive charge. And then sulfate, I do expect you to know that it's a SO4, 2 negative. This is 2 positive, this is 2 negative, so the correct chemical formula is CrSO4. All right. So with the new system, I do expect if you're given the name of the metal with the charge, you know it's this metal with that charge. All right. Now, we're switching gears here. Here, we're talking about covalently bound compounds, nonmetal to nonmetal. Now, they can be either pure covalently bounded, which we call nonpolar, or they can be unequal sharing of the electrons, which we call polar. But we are talking about covalently bound compounds, sharing of electrons. Notice we use the word molecules here. So for ionic compounds, we call them formulas. For covalent compounds, we call them molecules. They are discrete molecules, and they can be in a solid, liquid, and gas state. So examples of this would be H2, methane, CH4, water, H2O, carbon dioxide, CO2. Those are all covalently bound compounds that exist. All of those actually exist in the gas phase at room temperature, except water. Water is a liquid at room temperature. So you have to memorize this slide. It's not hard. Most of these you already know. Mono means 1, di, tricycle, tetras, tetra 4, pentagon, penta 5, hexa 6. Hepta may be the most, maybe you don't know that one. You definitely know a stop sign from first grade. Octagon, then nona for 9, and deca like decathlon for 10. So the only one I think it really kind of stands out you may not know is this one, but that's okay. So you should know the rest of these. Memorize these. These are important. These are important in order to name covalent compounds. Now, covalent compounding is real easy. The only thing it's not easy, and mono is not used consistently, and we generally omit it if it's the first element. But I'm saying we probably omit it a lot of times on the second element as 2. So they give this example. So if you only have one of the first nonmetal, you just name the name of the element, carbon. But the second nonmetal, if you only have one of them, you're supposed to use the term monoxide, mono meaning 1. But I'm going to tell you that's not used very consistently. I give you this example, but I rarely hear this substance called hydrogen monochloride. We just call it hydrogen chloride. Notice you still have an IDE ending. And the final vowel and a prefix is often dropped before the vowel of the stem name. So what they're saying here is that because mono ends in a O and oxygen begins with the valve, we drop the O off mono and combine it with the oxide, so we call it monoxide. That's what that's saying. All right, so let's look at this. Is so the naming is so easy here. Look, we only go to the next slide right into the naming. So silicon is silicon. Just name the first one, and then because there's no charges here, you have to tell the person how many of each element you have. So this is dioxide. Silicon, 2 oxygen, dioxide. This one, you got to tell the person there's 2 nitrogens, so dinitrogen, pentoxide. And now here's what we're talking about. Pentas got an A on the end, but because oxygen begins with the vowel, we call it pentoxide. Same thing here. We name the first element by its full name, chlorine, and then there's 4. It's one. Let's start that one over. Carbon, and then we got 4 of the chlorine, so we say tetra. And because chlorine begins with a consonant, we just say tetrachloride with the A intact there. Tetrachloride. Last one, iodine, and we got 7. That's hepta for 7, and then fluoride. And you're done. Very easy. I would say 90% of the students get this right on the exam. It's that easy. But spend the time on the ionic and the polyatomic ions. So here's some other examples. Now, these sometimes can be difficult. Let's talk about these. These molecular compounds, covalently bound compounds, have been around so long, they have their own names. Like, we don't call this dihydrogen oxide, which is what we would call it if we were following the naming rules for covalent compounds. We just call it water. Same thing here. We don't call this nitrogen trihydride. We call it ammonia. We call this ethyl alcohol. We call this glucose, or we call it a sugar. But we don't generally say hexacarbon, undeca hydrogen hexaoxygen. So we don't use those words. We don't say dihydrogen, pentahydrogen, oxide. We don't do that. So these have common names, and you do need to know these common names. Another one that you need to know is definitely methane. It comes up a lot, CH4. There are some tricky. This one is kind of tricky. We don't call it dihydrogen sulfide. We just call it hydrogen sulfide. That's what makes the rotten egg smell around a sewer plant or an egg. So we just call it hydrogen sulfide. Even though technically it's a non-methyl non-methyl, it should be called dihydrogen sulfide. I think those are the main ones. All right. So here, you're given the name, you write the formula, nitrogen monoxide, dinitrogen tetraoxide, diphosphorus pentaoxide, nitrogen trifluoride. See, those are really easy. They're telling you how many of each are present, and if they don't say, then it's understood to be one. Okay. Very easy. Like I said, most people get these correct. So what's the difference between ionic compounds and covalent compounds? Well, it is based on the bonding. Ionic bonded compounds versus covalent bonded compounds. So when you think of table salt or calcium chloride, which is hot melt, maybe you're using that today, they tend to be solids at room temperature. Ionic compounds, because there's such a strong electrostatic attraction between the positive ion and the negative ion, they bond so tightly, so strongly, that they tend to be, and they're in a formula, they are just atoms bonded to each other into a cube of atoms, and we've seen pictures of that, that they tend to be solids at room temperature. Where covalent compounds are solids, liquids, and gases. They can be any of these. The melting point is when a solid is converted to a liquid, and the boiling point is when a liquid is converted to a gas. The melting point and boiling points of ionic compounds tend to be much higher than covalent compounds. All right, so because of that strong attraction, and again, these are called intermolecular forces. Intramolecular forces. The stronger the intramolecular force, the stronger they tend to be, have higher melting points and boiling points. Intramolecular force. That's either ionic bonding or covalent bonding. So it takes a large amount of energy to break that electrostatic attraction. So ionic compounds melt at several hundred degrees Celsius. So ionic compounds are crystalline. Covalent compounds can be crystalline or amorphous. Amorphous means no regular structure. So let me give you an example of something amorphous. Sulfur, if you've ever seen sulfur powder, it's a yellow powder. And if you're taking the lab, you can ask the professor to show you an example of that. Glass is amorphous. So your glass windows, they're not crystal. Your glass windows are silicon dioxides, and they're arranged in a non-repeating pattern, and so that's called amorphous, no regular structure. Now there are crystals. When you think of like a diamond is a crystalline network solid, and it is covalently bound together. So that's why they're saying covalent compounds can be crystalline or amorphous. But think about this. You're heating up a table salt versus ice. They're both in the solid phase. You can see ice melt before your eyes once you get above 0 degrees Celsius. A diamond, you've never probably seen it melt. And generally it burns before it would melt. So that's the difference. Ionic compounds have very high melting points and boiling points. Now, this is really important too, and I don't think a lot of students spend enough time on this. Ionic compounds like table salt. So this is what table salt looks like. When you place it in water, it separates into these two ions. Well, these are ions to begin with. That was the ionic bonding that holds them together. So there's no chemical change here. All that's happening is the two ions are separating, and we have a name for that. That means dissociates. You go, why do I need to know this? Because once these two ions separate or dissociate, they have the ability to shuttle electrons between two electrodes. So if these are two metal plates, and I have this hooked up to a light bulb, and then I have an energy source here like a battery, and I connect it to this metal plate here, the sodium ions and the chloride ions can shuttle electrons back and forth between the two plates, and we have a complete circuit, and the light bulb glows. So electrolytes are substances that conduct electricity. That means there's ions present in the solution. That's what we have here. We have free-flowing ions that are able to move back and forth between the two electrodes, which allows conduction of electricity, the transfer of electrons from one plate to the other. Covalent compounds like sugar, so you know sugar, when it dissolves in water, it's still sugar. Covalent compounds tend not to form ions when they dissolve in water, unless they're a strong acid or a strong base or a weak acid, weak base. So the sugar molecule stays intact. It does not form positive and negative ions, and so it's a non-electrolyte. And that's going to be really important when we talk about colligative properties later on. Colligative properties are properties that depend on the amount of particles dissolved in a solvent like water. And this is why we generally, when we have ice on the road, we put sodium chloride on the road, or we put something like calcium chloride. So sodium chloride is NaCl. It dissociates into sodium ions and chloride ions. But calcium chloride is CaCl2. It dissociates into a calcium 2 positive ion plus 2 chloride ions. So notice we get more particles here when the calcium chloride dissolves in water versus the 2 particles that when sodium chloride dissolves. That's why calcium chloride works at colder temperatures. More ions dissolved in water, the lower the freezing point is going to be. And so when it gets really cold, sodium chloride will stop working as melting of ice but calcium chloride has a little bit lower temperature that it can work at correctly. So both of these, sodium chloride and calcium chloride, dissociate, and they are electrolytes. This is going to be important later on. Whereas most covalent compounds are going to be non-electrolytes. So here's a table. Just look at the table. Make sure you understand the difference. The main reason why we're doing this, we've taken the bonding, ionic bonding and covalent bonding, and now we're looking at the properties that we can see with our eye, like physical state, boiling, melting point, and boiling point. Yeah, that one maybe not so much a physical property there. I mean, that you can see with the eye, but you can definitely see the physical state and the melting point and boiling point with as a macro property. All right, we're going to stop here, and I will create another video for this part. So you have the information now to complete the naming part of the module. I think that's module 3.2. We've gone up to 3.4 here. So you have the ability to finish the naming and also start the next section. I will lecture on this section. I'll make a video for it. And then when we come back on Monday, we'll wrap up chapter 3 and get into chapter 4.